So which says in a cyclic process, furthermore, for a reversible cycle, so the first thing was convincing ourselves that the Clausius inequality actually holds. So what we did, we said, okay, let's prove it for a Carnot cycle and for a reversed Carnot cycle. So the Carnot cycle, we did the derivation, and the reverse Carnot cycle, I left it as an exercise. It's given in the book. So if you consider a Carnot cycle, it consists of two isothermal heat transfers and two adiabatic processes. So during the adiabatic process, delta Q is 0. So the adiabatic processes do not contribute to this integral. During the isothermal processes, the heat transfer occurs at a constant temperature, so that entire QH which is transferred is all at temperature TH. So instead of integrating, when you add up all the small delta Q's which are transferred, that adds up to the total QH divided by TH, because T does not vary. So QH by TH, and from the heat rejection again at constant temperature, that contributes minus QL by TL. And that we showed from our definition of thermodynamic temperature scale. This integral, the two contributions exactly cancel each other and we get 0. Then the argument was that any general reversible cycle can be considered as a superposition of a number of Carnot cycles. So essentially the argument runs this way, that in a Carnot cycle, the entire heat transfer occurs at a certain temperature. Now, if the heat transfer is occurring at varying temperatures, you split up the cycle into a number of subcycles, which where each of these subcycles has heat transfer at a certain temperature. So if you split it up into a number of small cycles which span a very small interval of temperature, then again you can, in each of these cycles, you can take T to be approximately constant during the heat transfer, and then you add up the effect of all the cycles, and then it again should give you this. Now this argument was not very clearly stated, so at the moment I'll just leave it as it can be shown. Now, once we know this, from a point 1 to a point 2, if you go by two different paths A and C and come back by the same path B, then if all the processes A, B and C are reversible, then this integral would be, so the contribution from A and the contribution from B would add up to 0, contribution from C and contribution from B would add up to 0. So A plus B gives 0 and C plus B gives 0, which means A and B must be equal. So, that holds for arbitrary choice of A and C. That means for any process from 1 to 2, the if the process is reversible, the integral of delta Q by T would be the same. So if I have an infinitesimal interval, so if my point 1 and point 2 have an infinitesimal are an infinitesimal distance apart in the thermodynamic coordinates, then I can take T to be approximately constant. So therefore, delta Q by T for a reversible process always has the same value as long as the endpoints are the same. So if I have an element delta Q, I go by different paths, the delta Q by T has to be the same. Now, that same element if I go that same element, if I go by a reversible path or by an irreversible path and return by the same path, then for the process A, if I consider that it goes along path A, which is a reversible process, and returns by path B, which is again a reversible process, then the entire cycle is reversible. So therefore, the equality must hold. So I have this. And if I go along C, so the C is an irreversible process. We denote it by dotted lines because the intermediate states are not equilibrium states, they are non-equilibrium states. So you could be having differences in pressure across the system. So there could be free expansion, or you could have temperature differences, jumps. So there could be heat transfer through a difference in temperature. So then the thermodynamic coordinates are defined for a system if it is in thermodynamic equilibrium. So there are no internal unbalanced forces or temperature gradients. So now I'm assuming that in the path C, the intermediate points are not equilibrium states. So I cannot define what the thermodynamic coordinate is, but this much I know, that it starts from the same equilibrium state as path A and finally reaches the same equilibrium state as the endpoint of path A. So the final points are states of equilibrium, but the intermediate points are non-equilibrium states. So then for the path going along C and returning along B, I have now this cycle is irreversible because the path C is irreversible. So if I have free expansion or heat transfer with the temperature gradients, then the heat transfer due to a gradient occurs one way, the heat transfer cannot occur in the other way. Similarly, the free expansion, a gas expands into vacuum, but it cannot contract back. So if you have a gas in half the chamber and you break the partition, it expands and fills the entire chamber, but it cannot spontaneously occur the other way. So then this process C therefore is irreversible. So for an irreversible cycle, we know from Clausius inequality this has to be 0. Now this and this are common. That means delta Q by T of C must be less than delta Q if the sum of these two is less than 0 and the sum of these two is 0. It means that this quantity must be less than this. And this argument uses the fact that path A is reversible while path C is irreversible. So therefore I can write now the argument was delta Q by T reversible. So then that if it is independent of path, it only depends on the endpoints. So we use this to define entropy, and this measures the change in entropy from the initial point to the final point. So now we have defined a quantity called entropy. The entropy is a quantity which depends on the thermodynamic coordinates. So if you have defined the thermodynamic state, that determines the entropy. So then every point in thermodynamic coordinates has a certain value of entropy associated with it. So therefore, if my endpoints are the same, then the change in entropy must be the same. Now, for path C and path A, the those were two paths. Path A was reversible, path C was irreversible, but the endpoints were the same. So therefore, the ds for both the paths is the same, but then the delta Q by T is not the same. It is less for irreversible than for reversible. So if we consider path A versus path B, versus path C. So it goes from one equilibrium state to another equilibrium state, but in between, path A goes through a set of quasi-equilibrium states, whereas path C goes through an non-equilibrium states. So then, since the final endpoints are equilibrium states, the ds for path A and path C are same. Since path A is reversible, because this is how entropy has been defined. Now, delta Q by T of path C is less than which means the ds is greater than delta Q by T of C. So ds is greater than so then we define a generation of entropy for an irreversible path So in this case, the delta Q by T is smaller, which we have shown from Clausius inequality. So if delta Q by T is smaller, then ds, so delta Q by T for irreversible is smaller than for reversible. Now ds is equal to delta Q by T for reversible. The delta Q by T is for irreversible is smaller, so we must add a delta S gen, which is the entropy generated in the irreversible process in order to get the change in entropy during an irreversible process. Now, in this course, we'll more or less keep this as something which is essential, but how to calculate the details of that will not work out. That involves quite a bit of complication. So all we know is the delta S gen must be a positive quantity if the process is irreversible. Okay, now just comparing with our first law. First law, we had done a similar derivation. We started from the concept that cyclic integral of Q minus W is 0. Just as here cyclic integral of delta Q by T is 0, we had started with that over there. And then use that to define a quantity called energy. Now, after defining energy, we further stated that the energy has two types of contributions. One is the macroscopic and the other is the microscopic. So the macroscopic consisted of the kinetic and potential energies, while the microscopic in our case was internal energy. You could have some other contributions like chemical energy, nuclear energy, etc. So now a similar question would arise. We have defined something called entropy. Now there again we had said that the macroscopic and the microscopic, they again have a difference. The macroscopic depends on the macroscopic coordinates of the system. The kinetic, the potential energy depends on the position of the center of mass. The kinetic energy depends on the velocity of the center of mass. On the other hand, the microscopic part, the internal energy did not depend on the external coordinates. It depended only on the internal random motion, and therefore that depended on the thermodynamic coordinates like temperature and pressure. So depending on the temperature and pressure, that would determine how much of a motion is there in the how much of energy is there in the random motion of molecules in the material. So it was the internal energy which was a thermodynamic function, as different from the kinetic energy and the potential energy, which depended on the gross position and velocity of the material. So once again, a similar question would seem to arise, that this entropy which we have defined, does it again have a microscopic and a macroscopic component? So then we have to base our argument on what the entropy represents. So there, the statement which is made in a book, we have to take it as a statement because a more convincing argument is difficult to give, that the entropy is a measure of the disorder in the system. So then it is disordered motion or random motion which contributes to the entropy. So the more random it is, the more the entropy. Now, if you want to go to a quantitative measure of disorder, then you would have to go into details of the microscopic description. Now that mathematics is far more complicated than what we are discussing. So it would not be possible to cover that in a basic thermodynamics course. But from that, what we can sort of vaguely understand, that it is disordered motion which is contributing to entropy. Now let's have a look at the contributions which were there from gross motion in the to the energy of the system. So apart from internal energy, there were contributions from the potential energy and the kinetic energy. Now potential energy depends on the position. Now the position is not something which we would expect would contribute to the amount of disorder in the system. Similarly, the kinetic energy is the gross motion of the material in its entirety. That again is one velocity, so one well-defined velocity, that again we expect would not contribute to disorder in the system. So therefore, unlike the energy which had contributions both from the random motion and from the gross position and motion, the entropy has only contribution from the random motion, which which depends on the thermodynamic state of the system. So therefore, unlike the first law, where we had the kinetic energy and the potential energy also contributing apart from the internal energy, in the second law, we do not have any such thing. The entropy is entirely because of the thermodynamic state of the system. Now, having said that, we'll come back to the statement to what we said at the end of the class, that okay, we have a formal definition for entropy, but can we actually see entropy being calculated? Given a certain material at a certain temperature, if I increase its temperature, keeping either volume constant or keeping pressure constant, then we know how to calculate what is the change in the internal energy or the enthalpy of the system. So provided we know the value of the specific heats, we can calculate by how much the internal energy or the enthalpy has changed. So if we arbitrarily set internal energy or enthalpy to have a certain value at a certain temperature, given any other temperature, we know how to calculate the internal energy at that temperature. So once again, that's a simple relation. So if you know at a certain temperature, you change the temperature, the Cv into delta T gives you the change in internal energy. So it's a linear relation between internal energy and temperature if the specific heat is constant. If it's not constant, in that case, you have to integrate. Depending on what the variation is, that will determine what the integral is. So now, how do we calculate entropy as a function of temperature, and what is the expression for entropy as a function of temperature if we assume that specific heats are constant? Again, entropy uh, is an extensive quantity. If I calculate the value per unit mass, in that case, the value is called the specific entropy. Where delta small q represents the Q added per unit mass. So here the expansion is usually negligible. So then the PdV, that contribution can be neglected. So since I'm neglecting something, that is why the approximately equal to, this is equal to du divided by T reversible. So Now, since it's a reversible process, the temperature at which the Q is being transferred must be the temperature of the solid or the liquid itself, so that the heat transfer is occurring in a reversible manner. So the du would be C dt. So although the per unit mass values for thermodynamic quantities are represented by lowercase letters, small s, small u, small h for the specific. So small u is specific internal energy, small h is specific enthalpy, and small s is specific entropy. Unlike that, when I look up the book, I find that the uh, the specific heat, which is the energy required per unit mass per unit change in temperature. So the specific heat is even when it's per unit mass is denoted by a capital letter. That seems to be the convention. So then the change in internal energy would be the specific heat into dt. The change in specific internal energy would be this. In the case of a solid or liquid, we do not distinguish between a specific heat at constant volume and constant pressure. So the du would be this divided by T. So then if I assume that C is constant, so unlike the specific internal energy or specific enthalpy, which was a linear function of temperature, the entropy is a logarithmic function of the temperature. So once again, since I'm calculating change in specific entropy, so I have to take change in specific internal energy and pressure into change in specific volume. So the U and the V are lowercase. For an ideal gas, the internal energy is a function only of the temperature. As the book explains, the subscript 0 here represents that it's an ideal gas. So then the change in internal energy is specific heat at constant volume into the change in temperature. We have if the gas constant is expressed as per mass rather than per mole, then this is the relation. Now, if I divide by m, then it would be but then volume by mass is specific volume, volume per unit mass. P by T So if I know the entropy of a gas at a certain temperature and volume, at any other temperature and specific volume, I can use this relation to calculate what is the entropy at that value. So if I know S1 at a certain T1 and V1, given a certain T2 and V2, I can calculate from this what is the value of S2. Alternatively, this we had shown when we discussed enthalpy. So then Now we have so this is an alternative expression for entropy change. Earlier we had in terms of temperature and specific volume. This is in terms of temperature and pressure. Now from this we can deduce a relation between pressure and specific volume for an adiabatic process. So if I have an adiabatic process, in a reversible adiabatic process, the entropy change is 0. So because for a reversible process, the change in entropy must be equal to integral of delta Q by T. So for a reversible So a reversible adiabatic process is an isentropic process. Now let's say I have I have a reversible adiabatic process occurring for an ideal gas. In that case, from the two relations which we derived, we know that this quantity must be equal to 0. Alternatively, the other quantity in terms of Cp0 also must be equal to 0. So Cv0 ln So if I divide the second by the first equation, this is the ratio of specific heats, which is usually denoted by gamma. So then so it gives us the relation which an adiabatic, a reversible adiabatic process must satisfy. So I think I'll close at this point. One of you had a doubt about that first law derivation.
No, sir, it got cleared. Thank you.
It got cleared, okay.
Yeah.
If you have any questions, you can ask. Let me take attendance. Okay, so tomorrow we'll be having the class test. So let me just mention what are the requirements. You should be ready with paper and pen to write an exam in the conventional way. Second requirement is all of you have to log in to MS Teams and keep your camera on for the duration of the test. This is what instructions have been given to us. And so if somebody is not logged in, then you are in principle not officially attending the class test. So that should not happen. Everybody should log in. And for the Steam tables, I had sent it to you by email. I hope all of you have that with you. If not, I could send it once again, but I presume all of you have it with you. So then the Steam tables in different references have minor differences, usually in the last place. So what I would recommend, since I'll be checking with values calculated by my program, and there the it's not possible for me to redo for every student because the values will be different for different students. So therefore, for your result to match my result, I would recommend that you use the Steam tables which I had sent to you. So then it will use the same values which I am using for calculating what is the correct answer. And have some arrangement for scanning your entire answer script, because your entire answer script would have to be scanned in the extra 10 minutes which you will be provided for that purpose. So we'll start probably tomorrow at 11. Huh. So I'll give you 10 minutes. Now it's not possible for me to ensure that nobody starts within the next 10 minutes. So what I'll say, I'll distribute those question papers, and after distributing, probably I'll give you the instructions. Although the instructions are given on the first page, I'll explain them once, since I have a slightly unconventional way of conducting the exams. So I'll explain it to you once. Now after that, it's up to you when you start. And so the time allotted is 1 hour 30 minutes for writing the paper, plus the 10 minutes for given to you for reading instructions. So it will be 1 hour and 40 minutes. So within that 1 hour and 40 minutes, within that deadline, the final answers would have to be emailed to me. So this time I'm asking you to email all the answers to my Gmail address, because I don't, at least the Gmail address doesn't have a risk of overflow. So there, the limit on storage is probably much higher than it is for the IIT email. So I'll send you the question papers again from that, so you can use the reply mode also. So the how to name your files that I have already explained, and the question papers will be numbered serially, so it will be Q paper 01, Q paper 02, so it will be Q paper 01.pdf, Q paper 02.pdf, depending on the serial number in the roll list. So before the exams, I'll send you the roll list. So in the roll list, check what is your serial number. So then pick up the question paper which has that particular serial number, and on top it will be written for roll number and name. So just confirm that the question paper which you have picked up is the one which is meant for you. So that is about instructions. If you have any questions, you can ask. Okay, then we'll close today. All the best for the exams.